Hello learners, welcome to this tutorial on Arduino Mega Board programming and simulation. In this video tutorial, I will be discussing about on how to use an interrupt, how to configure it and program it for an application. So interrupt. Interrupt is a signal generated by a hardware or software when a process or an event requires an immediate attention. So for example, we have internal peripherals and external peripherals connected to your Arduino Mega Board. So the internal peripherals are analog to digital converters, timers or counters, UART, SPI, I2C. So this UART, SPI, I2C are serial communication protocols, comparator, etc. So these are the peripherals available inside your Atmega 2560 microcontroller. Same way, we can also connect some peripherals outside of your Atmega 2560 microcontroller, which can be something like a switch, keypad, keyboard, joystick, or a mouse. So this internal peripherals or external peripherals can generate an interrupt. Same way, an hardware, software can also generate an interrupt. Something like a divide by zero can generate an interrupt. Something like an illegal opcode can generate an interrupt. So software based interrupts are called as an exception, and exceptions can also be serviced by a CPU. So whenever this peripherals needs to use your CPU, it will make a request. Upon request, the CPU will provide certain time for the execution of the interrupt service routine. So interrupt service routine is nothing but the program related to this hardware or software interrupt, which will service that interrupts. Let us now see the mechanism behind the interrupts. So let us take a CPU is currently executing certain instructions. So it is taking instruction 1, completes it, goes to instruction 2, completes it, goes to instruction 3, like that it is doing certain operation. So when it is executing instruction 4, let us assume an interrupt gets occurred, due to which what happens, first the CPU will complete the instruction 4 execution, then it will go to the ISR, interrupt service routine. So interrupt service routine is nothing but the program related to the interrupt. It executes the interrupts. Upon completion of the ISR, it again comes back to the main program and it resumes the work where it left off. So whenever there is an interrupt occurrence, we need to switch over our program control from main program to the ISR. So during which we need to save certain context. So context is nothing but the important registers associated with your main program and also the program counter value. So program counter will indicate the address of next instruction which will be executed by the CPU. So those information we need to save it before moving on to your ISR, because upon completion of an ISR, we need to come back to our main program. So when I want to come back to the main program and resume flawlessly, then we need to have this information. So after completing the ISR, we retrieve those information back and we try to resume the operation seamlessly. So the saving of the important registers and program counter value can be done into a registers or to a stack memory. So this process is called as a context switching. Same way, after completing your interrupt service routine, we need to bring back that context to the original register content. So this is context retrieving operation. So there is a requirement of a context switching and context retrieval whenever there is a interrupt occurrence and when an interrupt gets serviced. Same way, if multiple devices generate interrupt at the same time or with some small time delays, then we need to have a certain mechanism so that only one particular interrupt will be serviced by the CPU at a particular time. So in order to do that, most of the microcontrollers will have an interrupt controller. So this interrupt controller, it will receive all the interrupts from the devices, and depending upon the priority of the interrupt, a particular interrupt will be sent to the CPU, and the CPU will start servicing that interrupt. So the role of selection of interrupt and the ISR address provision can also be provided by the interrupt controller. In this video, I will be discussing about an external interrupt and how to capture this status of an external interrupt by varying the status of the LED. So we are going to connect a switch to pin number 21 of your Arduino Mega Board or Atmega 2560. So this pin number 21 is an interrupt pin. So whenever we press a switch, interrupt will be generated. Upon this interrupt, we try to change the state of your LED connected to pin number 30. So as I said, this pin number 21 is a interrupt pin and it is a INT0 pin. So total of 6 external interrupts are supported by your Arduino Mega Board, which can be named as interrupt 0 to interrupt 5. So INT0 is at pin number 21, INT1 is at pin number 20, INT2 is at pin number 19, and INT3 is at pin number 18. INT4 is at pin number 2 and INT5 is at pin number 3. So these are the external interrupts. So we can connect up to 6 external peripherals which can cause an interrupt to your CPU. And this interrupt can occur on different triggering options. Either I can have a low signal in the interrupt line which can cause an interrupt, or I can have a change in the interrupt line, either a rising edge or falling edge can cause an interrupt, or only rising edge or only falling edge can cause an interrupt. So few things you have to remember while programming your interrupts. In an ISR, the delay function will not work. Usually we use this delay function to create an interval between certain operations. So this delay function will not work inside your ISR. Same way, whenever we declare certain variables which we will be using in our ISR, it should be declared as a volatile variable. And while executing an ISR, whenever there is a serial data is being received, so those data will be lost. Same way, the millis function will be used for creating certain time delays, will not get incremented outside of your ISR when it is used inside the ISR. And another important aspect of your interrupt is we need to know about the priority of the interrupt. So priority of the interrupt is decided based upon the vector table address for a particular interrupt. For example, here I have shown certain interrupts with their vector table address. So vector table is nothing but a location in your program memory where the jump instruction for your ISR is located. So for example, in case of a reset interrupt, our CPU goes to this address location 0000 where it finds an instruction jump to the address of your ISR for reset. So it goes to that ISR and it starts executing. Same way, in each and every locations here in the program memory, initial locations in the program memory, it has a jump instruction. So jump instruction to the ISR of your particular interrupt. So depending upon the address location of an interrupt in the vector table, its priority is defined. So the interrupt which is having a lower vector table address has a higher priority when compared to the interrupt with higher vector table address. So for example, reset as a higher priority when compared to INT 0. Same way INT 0 as higher priority when compared to INT 1. Same way it goes on like this. INT 2 as higher priority when compared to INT 7, and INT 7 will have higher priority when compared to watchdog timer. So like that, the interrupts are being prioritized in an Atmega 2560 microcontroller. Now let us dive onto the programming part. For developing a program, embedded C program, we will be making use of the Arduino IDE environment, and to build the circuit and test the logic, we will be making use of Proteus 8 simulator. So let us go to Proteus first for building the circuit. Let me create a new project. First, select the location where we are going to save our project. I'll give a name as interrupt. Select the folder and give a name for the project. Press next. Select a schematic for building the circuit. I'm going to use a default schematic. You can change the size of the schematic either in a landscape mode or in a portrait mode. We have different sizes of the schematic. You can change it according to your wish. Press next. We are not going to create any PCB layout, so I'm going to leave it as it is. Press next. We are not going to use any firmware. Press next. Here you can see only the schematic is selected. Press finish. So we will get the schematic window where we are going to build our circuit. In order to build the circuit, the first thing which we need to do is we need to select the components. For selecting the components, I go to pick device. In the keyword, let me type Arduino. Select Arduino 2560. Gets added to your list. Then we require a LED. Let me select an animated version of an LED. Let me take blue color LED. Then we require a switch. So let me take a push button. Here I have a SPST push button. Add it to the list. Then we might also require a resistor. Add it to the list. So these are the components which we require for this program. Once we have selected the components, press OK to come out of the window. So now we have the component selected. We have to use this component to build our circuit. Press Arduino Mega, put it onto your circuit. So here if you see, I have pin number 21 is your INT0 pin, which is an external interrupt pin. Same way pin number 20, INT1, pin number 19, INT2, and pin number 18, INT3. Same way pin number 2, I have INT4, and pin number 3, I have INT5. So these are the 6 external interrupt pins. For this program, we are going to use INT0 pin for our external interrupt. So let me connect the switch push button to this INT0. So I am placing the push button, connecting this to pin number 21. Then usually the pins will be in high impedance state. Whenever I press it, it might go to a 5 volt. This is not a valid interrupt signal. So in order to have a valid interrupt signal, either I should have a low to high or a high to low. So the pin should be retained at low. Then it should go to a high state, thereby I can use it for a interrupt. So let us use a change interrupt. Either a rising edge or falling edge will create an interrupt, which means I should have a transition from 0 to 5 or 5 to 0 volt. So in order to do that, I am going to use a resistor and connect the resistor to a ground so that this pin go to terminals mode, select a ground, place it onto your circuit, connect the resistor. So now what happens is, first let me complete the power supply also for the switch. So now what happens? This pin by default it will be at 0 volt. Whenever I close the switch, the supply will current will flow through this terminal. Thereby this pin will be at logic 5 volt. So we will have a transition from 0 to 5 volt. Whenever I release a switch, what happens? Again there will be a transition from 5 volt to 0 volt. So this can be used as a valid interrupt signal. So we need to connect a resistor to a ground so that this pin by default will be maintained at 0 volt. Whenever we press a switch, the pin will go to high, which is 5 volt. And upon releasing of the switch, the pin will go to 0 volt from 5 volt. So next thing which we are going to do is connect a LED to pin number 13. So again go to the components board, select an LED, place it onto your circuit. Anode of the LED gets connected to pin number 13 and cathode I am going to connect a ground. So go to terminals board, select a ground, place it onto your circuit, connect it to your LED. So this completes our circuit part. So we have connected a switch to the interrupt pin. Upon the status of the switch connected to the interrupt pin, the LED will change its state. So that is what we are going to do in the program. So let us save this schematic. Now let us go and discuss about the embedded C programming part. So here when we start with, first we define the pin number 13 where we are going to connect our LED as an integer variable. So as I said, whatever variable which we use in our ISR should be declared as a volatile. So for that purpose I am going to use a variable named state in the ISR. So this is declared as a volatile int variable state, and by initializing it to low. Then we have a void setup function which runs for only for one time, and usually it will be used for configuration purpose. Since we are connecting a LED to pin number 13, this pin number 13 should be configured as an output pin. So for that we make use of this pin mode, pin number 13, and it is configured as an output pin. Same way to configure the interrupt, we use a function called as attach interrupt. So attach interrupt, and which pin we are going to use it as an interrupt pin? We are going to use the pin number 21 as an interrupt pin. So in order to use this pin as an interrupt pin, first thing is we need to convert this pin from a digital pin to an interrupt pin. So we are saying that the pin number 21 we are going to convert it from digital pin to an interrupt pin. Then we specify the ISR program. So here we give a name as blink, which is a ISR program for this interrupt connected to pin number 21. And what should be the logic of the interrupt? It is change interrupt. You can give a low, rising, falling, or change. Change means either a rising edge or falling edge will cause an interrupt. Once the configuration is done, we go to the loop statement where I am going to write the pin with the state. Right? So by default, what happens when I switch on the program? The initial state of the state is low. So the pin will be at low, the LED will be off. If an interrupt occurs, which means we have pressed the switch, when an interrupt occurs, automatically we go to the ISR. ISR is blink. We have a function written here. This is our ISR. So whenever switch is pressed, we go to the blink ISR. Here in blink ISR, we change the state. Exclamatory mark indicates not. Not means it's one's complement value. 0 means it will change to 1. 1 means it will change to 0. So not of state. So if initial state is 0, it will change to high. If the initial state is high, it will change to 0. So there is a change in state. So after completing the ISR, again it will come back to the main program of executing this digital write. So whatever state it has changed, it will get reflected in your pin number 13. So that is how this program works. So now let us try to save this program. Let us try to save this program. LED interrupt.c, save, and try to convert this program into a hexadecimal file. Go to Sketch, export compiled binary. This process will do two things. One is compilation, and it will convert this embedded C program into a hexadecimal file. So once this is done, you can see the status. There is no errors. We can go to your Proteus environment and dump our code hexadecimal value into the microcontroller. So right click on the microcontroller, go to edit properties. Here you can select the program file. So we are trying to import the hexadecimal file into your program memory of your microcontroller. So go to the location, select the hexadecimal file, press OK. So now we have imported our hexadecimal file into the program memory of microcontroller. Now let us check the logic, whether it is working properly or not. In order to do that, go and press this play button. So right now the circuit is being implemented. You can see now the switch is not pressed, so LED is in off state. When I try to press the switch, you can see the LED starts glowing. When I release the switch, the state changes. So now the LED status gets changed depending upon our interrupt signal connected to the pin number 21. So that is what we try to do in the program. So this is a very simple mechanism by which an interrupt can be communicated to the CPU. Upon interrupt, the CPU responds to that interrupt signal. To stop the program flow, press the stop button and you can come out of the program. So in this tutorial, we have discussed about on how to configure and program an external interrupt with your Atmega 2560 microcontroller. Thanks for watching. Please subscribe for more technical learning. Thank you.